Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Sridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today we will discuss one another important board exam topic on radioactive decay, and we'll learn half-life of radioactive decay and understand how numerical problems are solved related to half-life conditions, and we'll also understand what is average life of radioactive decay. So let's start. In another video, we have understood law of radioactive decay given by Rutherford and Soddy. According to that, if n is number of radioactive nuclei, then rate of disintegration or rate of decay of radioactive substance, change in active number with respect to time, is directly proportional to the number of radioactive nuclei available. So higher the present number of radioactive nuclei, higher would be rate of disintegration, and this proportional relation is converted into equality using a constant, decay constant. Higher value of decay constant indicate higher value of rate of disintegration, and this negative sign clearly indicate that with increase of time the present number decreases. So this dn by dt is a negative ratio and decay constant is a positive parameter, and this negative sign match that mathematically. Now this differential equation can be applied to a shorter, smaller duration. To use this relation for a longer duration, we have separated variables and perform integration, and after integration we got that present number of radioactive nuclei at any time t in terms of initial number is given by this exponential decaying relationship, and this characteristic clearly indicate that as time increases, present number exponentially decay. In the radioactive decay process, due to disintegration or decay, the number of present radioactive number of radioactive substance continuously decreases with respect to time in an exponential manner. When the number are higher, the rate of decrement of present number is also higher, and as number decreases, rate of disintegration or decay also decreases as slope of number and time changes with time. Now the time interval in which present number of radioactive nuclei reduces to half is known as half-life period, denoted by T half, TH. So in this relation of radioactive decay, in time t equal to t half, the present number become half of initial number. So present number become half of initial in t equal to t half. Now n note, initial number of radioactive nuclei, get cancel out from both sides, and when we invert this relation, we can say e raised to power lambda t half is equal to 2, where lambda is decay constant, denote disintegration process. Now to remove this exponent power, natural log and exponent are inverse function of each other. So to both side, natural log is taken out. So natural log e raised to power lambda 2 become natural log of 2. Now exponent power and natural log are inverse function of each other. They will remove each other effect, and this first number on which first function is operated become the result. So lambda t half become equal to natural log 2. Now natural log 2 can be converted into log with base 10 using natural log 10, and natural log 10 is 2.303. So the product of decay constant and half-life with log 2 value equal to 0.3020 becomes, after multiplication of 2.303, 0.6931, and we can remember it. 1 3s are 3, 3 3s are 9, and 3 2s are 6. This value is roughly near to 0.7, and it is 0.6931. So the product of decay constant and half-life is constant, and its value is natural log 2 or 0.693. As product of decay constant and half-life is equal to natural log 2 or 0.6931 is a constant. So out of decay constant and half-life, if one is known to us, we can find out other one. We know that radioactive decay is a self-stimulated continuous action, and it can't be controlled by any of the external mean. And for a particular nucleus composition, decay constant is constant, and that define decay process. So as decay constant is constant for a particular nucleus composition, half-life is also constant for that particular nucleus composition. That means in same time interval, the present number reduces to half of its initial value at every instant, and the value of half-life or decay constant can't be changed by any of external means, physical or chemical, or even they won't change with time. So the value of half-life will not change with time. So in each half-life, whatsoever present value, after one half-life, that value will reduce to half of that, and different nucleus composition got different value of half-life period. Polonium, which is very active radioactive substance, got a very small value of half-life. So its half-life is smaller, so decay constant is higher. So rate of decay of polonium is very high, and in fraction of second you will find that polonium will become negligible small, whereas radon-222 got a higher value of half-life period, 3.8 day, considerable in duration. So compared to polonium, its rate of decay is smaller as its decay constant is smaller. Radium-226 got a considerable half-life period, 1620 years. So in 1620 years, whatsoever its present value will become half, whereas in carbon-14, the half-life is 5760 years. So in a fossil sample, the amount of carbon-14 will reduce to its half amount in 5760 years, whereas uranium-238 got a very small decay or disintegration rate with a very high amount of half-life, 4.5 into 10⁹ years. And if we presume that in the start when our earth is formed, the two isotopes of uranium, uranium-238 and uranium-235 are equal in amount, and the present ratio of uranium-238, which got smaller rate of decay and higher amount of half-life compared to uranium-235, which got half-life 10⁸ years. The present ratio of uranium-235 is just 0.07%. So it indicates that earth formation got less than 2 half-life of uranium-238, and we can predict the life of earth from ratio calculation of uranium-238 number and uranium-235 number. For a stable nuclei which won't decay with time, got a zero value of decay constant, so its half-life is infinite. It is given that half-life period of uranium-238 is 4.5 into 10⁹ years, and it is asked how much fraction of it will decay in 1 year. So 1 year duration is very small compared to half-life period. So we can use the differential derivative form of decay relation. So according to differential format, rate of disintegration directly proportional to number of present atom, and the proportional constant is decay constant, or decay constant is defined as fractional rate of disintegration per unit of time. So if we know decay constant in a certain time interval, we can find out fractional amount of decay as product of decay constant and time interval. And if we take time interval 1 year, then fractional rate of disintegration dn by n is equal to decay constant, and the product of decay constant and half-life is constant, natural log 2 or 0.6931. So we can say decay constant is 0.6931 divided by half-life, and half-life of uranium-235 is 4.5 into 10⁹ years. And when this ratio is solved, the fractional decay amount will become 1.5 into 10⁻⁻10. Fraction will decay in just 1 year. So uranium-238 got a relatively smaller rate of disintegration or decay, as its half-life is very considerable in duration. We can derive a very useful relation for numerical calculation. The present number of radioactive nuclei at any time t in terms of initial number and node is given by this relation, where lambda is decay constant. So we can say the ratio of present number and initial number of a radioactive substance is equal to exponent power minus lambda t. Now at half-life time period t equal to t half, this ratio present number become half of initial number, so the ratio become half, and half is equal to e raised to power minus lambda t half. Now this e raised to power minus lambda t, this t can be converted as by multiplication of t half in numerator and denominator as this expression, and from above relation e raised to power minus lambda t half is equal to half. So we can say the present number and initial number at any time t, if t half is half-life, is t over t half power of 1/2, and this mathematical expression can be written as present active mass of radioactive substance to initial mass of that substance, or present active number of radioactive nuclei to initial number of radioactive nuclei, or present level of activity or rate of disintegration to initial rate of disintegration or initial activity as half raised to power T over T half, where T half is half-life of radioactive substance and T is the time of present calculation. So if we know half-life period of radioactive substance, we can find out ratio of present and initial mass, number or activity at any time T, or we know the ratio of present and initial mass, number or activity at any time T. We can also find out half-life period, and calculation of this relation is specifically become very simple when the time of study T is multiple of T half and the ratio of time of consideration and T half is 1, 2, 3, 4, 5 or 10. The denominator of right hand side 2 raised to power n become 2 raised to power 1 2, 2 raised to power 2 4, 2 raised to power 3 8, 2 raised to power 4 16, 32 or 2 raised to power 10 is 1024, but for simplification we can convert 2 raised to power 10 as 1k or 1000. So for time t equal to 1 half life, the ratio of present number to initial number is only half, so the number reduces to half of initial value in 1 half life. In 2 half life it become 1/4. In 3 half life the present number become 1/8 of initial number or become 12.5% of initial number. In 4 half life it is 1/16. In 5 half life it is 1/32 or just 3.125%, and in 10 half life it become just 1 millifraction or 0.1%. Practice of some numerical questions will make application of this expression quite friendly. For a radioactive substance, the 7/8 fraction of radioactive substance will decay in 6 hours. It is given to us. Then what will be the time for the decay of 15/16 fraction of the same radioactive substance? That we have to find out. So this question is related to half-life period calculations, but our relation of half-life period relate present number to initial number. So we have to find out present undecayed fraction from this decayed fraction. So after 6 hours, the present value n is initial number minus decay fraction, and decay fraction is 7/8 of initial. So the remaining amount is just 1/8, and 8 is 2 raised to power 3. So it indicates that this present amount of 1/8 is a case of 3 half-life. So 6 hours is a duration equal to 3 half-life. So half-life is 2 hours. So from this information we have obtained the value of half-life, as we know the ratio of present number and initial number as 1/8, and 8 corresponds to 3 half-life, and 6 hours when is 3 half-life, then 1 half-life will become just 2 hours. Now again, to find out time for the decay of 15/16 fraction, we have to find out undecay amount corresponding to decay of 15/16 fraction. So initial number n0 when subtracted from total decay amount, then we'll get present amount of radioactive substance equal to n0/16, and we know 16 is 2 raised to power 4. So this case of 1/16 amount of present amount or 15/16 part of decay amount is a case of 4 half-life, and 1 half-life is known to us 2 hours. So the time for the decay of 15/16 fraction of radioactive substance is 8 hours. 4 into 2. In a sample of radioactive substance, the number of active nuclei will remain only 12.5% of its initial value in 6 hours. That means in 6 hour duration, the number of active present nuclei will become only 12.5% of its initial value. We have to find out half-life of this radioactive sample. So here 12.5% means 12.5 divided by 100 or 1/8. Now 8 is 2 raised to power 3. It means this condition of 6 hours is a condition of 3 half-life, as after 3 half-life, the present amount will become 1/8 or 12.5%. Now 6 hours is equal to 3 half-life. So 1 half-life is equal to 2 hours. So half-life of this radioactive sample is 2 hours. It means this sample will become half after 2 hours, become half of half or 1/4 or 25% in 2 half-life, that is after 4 hours, and after 6 hours it become 1/8 or 12.5%, and after 4 half-life it will become 1/16, and after 5 half-life or 10 hours it will become just 3.125% of its initial value. One radioactive substance has a half-life period of 24 days and its 32 milligram material amount is present in a box. Now how much of its amount present in box will get decay in 120 days? So this duration of 120 day with half-life 24 day is a case of 5 half-life, as 5 times of 24 is 120. Now the present amount after n half-life become 2 raised to power n fraction of initial amount, and for n equal to 5 the present amount will become m naught by 2 raised to power 5. 2 raised to power 5 is 32 and initial amount is 32 milligram. So the present amount after 5 half-life or after 120 days is just 1 milligram. So the total decayed amount of this radioactive substance, which was initially m naught and presently m, is the difference of m naught minus m, or 32 milligram minus 1 milligram, or 31 milligram. Mean life of a radioactive substance is also very important in decay process. The disintegration or decay of radioactive substance is a self-stimulated and continuous process. It can't be controlled by any of the external physical or chemical means. And this process is a random process, but for a group it obeys statistical relations. In a radioactive decay process, it is fixed that in 5 half-lives, out of 32 present atoms, 31 will disintegrate or decay in another daughter compositions, and only one nuclei out of 32 radioactive nuclei will remain present or active after 5 half-lives without decay. So there is a fixed probability of decay in 5 half-life. It is 31 by 32 fraction, or there is a fixed probability of undecay, 1 only out of 32. But it is not fixed which out of those 32 atom will remain undecayed, or out of 31 which get decayed, which one will get decay first. Everything is random and one cannot predict or tell about a particular atom whether that will decay or not decay in a certain specified time. As in this random phenomena, decay or disintegration of a radioactive nuclei depends upon the chance, upon probability, and the process is governed by the law of probability. Since nuclear radioactive decay is a self-stimulated continuous action, so the probability of decay or undecay can't be controlled by any means, or in other words, the half-life period of a radioactive substance will not change with the change of physical conditions or chemical composition, or even with the change of time. The nuclei or atom which decay or disintegrate earlier has a shorter lifespan, while those nuclei which disintegrate later on has a longer lifespan. So average life of radioactive nuclei is a ratio of sum of lifetimes of all atoms and total number of radioactive atoms. Now a small elemental dn amount disintegrate after t time, then sum of lifetimes of all atom can be obtained by integration, and if we divide it by initial number of radioactive nuclei, then this become average life of radioactive substance, and mathematically if we manipulate and calculate this ratio, then it comes as inverse of decay constant. So average life or mean life of radioactive substance is inverse of decay constant, and the product of decay constant and half-life is natural log 2 or 0.693. So average life is half-life divided by 0.693, or this ratio is 1.4 times half-life. So average or mean life of radioactive substance is 40% more than its half-life. For a radioactive substance having initial radioactive nuclei number n naught, the present active nuclei number at time t is given as n equal to n naught e raised to power minus lambda t, and after one average lifetime for t equal to t average, the present number is given by this n naught e raised to power minus lambda t average expression, and t average is inverse of decay constant. So product of decay constant and t average become 1, and the present number after one average lifetime is n naught by e, and 1 by e is 0.368. So present number after one average lifetime is 36.8% of initial number. One can remember this 0.368 figure as 3 2s are 6 and 6 and 2 is 8. So present number will become 37% of initial number after average lifetime. So the total decayed number after one average lifetime can be obtained as initial number minus present number, and present number is 36.8% of initial number. So the difference become 63.2% of initial number. One, again remember this figure 0.632 as 2 3s are 6. So after one average lifetime, the total present amount is 37% and total decayed amount is 63%. Now, as expression of average or mean life says inverse of decay constant, or as product of decay constant and half-life is natural log 2 or 0.693, we can say that average or mean lifetime of radioactive substance is 40% more than its half-lifetime, and in half-lifetime the total decayed amount is only 50%, and in extra 40% time the total decayed amount will become 63.2%. so more amount will decay in more time, as average or mean life of radioactive substance is more than its half-life. In one half-life the 50% amount will decay, and in mean life 63.2% amount will decay. In a certain radioactive substance, the present active amount will become 1 by 64 fraction of its initial amount after 15 hours. Then we have to find out its half-life, average life and decay constant. So we know the present amount is 1 by 64 fraction of initial amount, and 64 is 2 raised to power 6. It means this given condition of 15 hours is a case of 6 half-lives, and as given 15 hours is 6 half-lives, so one half-life is 1/6 of 15 hours or 2.5 hours. Now we can convert hours in second. 1 hour got 3600 seconds. So this duration of one half-life is equal to 9000 seconds. Now decay constant, half-life and average life, all three are interrelated. So if out of three any one is known, we can find out other two. As half-life is 9000 seconds, the product of decay constant and half-life is natural log 2 or 0.6931. So decay constant is 0.6931 divided by 9000, that is half-life, and the unit of decay constant is 1 by second, and average life is a inverse of decay constant, so it become 9000 divided by 0.6931 and its unit is seconds. We hope this informative learning video has explained each and every aspect of half-life and average life of radioactive decay, and if your time of study got a integer multiplicity with half-life time, then you can relate present and initial mass, number or activity level by this useful relation, and can make numerical calculations often asked in our examination. Our other learning video of the same playlist are equally useful, and if you need our exam-centric notes and support and help of online doubt clearing classes, do join our YouTube channel membership by clicking join button just beneath. Happy learning, have nice time. Thank you very much.